Beneath Yellowstone's iconic geysers and hot springs, a world of extraordinary geological activity is constantly unfolding, hidden from the eyes of millions of visitors who marvel at the park's surface wonders. Deep below lies a supervolcano of immense power, one of the largest and most closely studied volcanic systems on Earth. For years, scientists have mapped its vast magma chambers, tracked subtle ground movements, and monitored the heat and gases that escape to the surface, all in an effort to understand what lies beneath. In April 2025, a breakthrough changed our understanding forever. A hidden magma cap was discovered, sitting above the main reservoir, previously undetected by even the most advanced instruments. This cap, a remarkable layer of partially molten rock mixed with superheated fluids, acts much like a lid on a simmering pot, trapping heat and pressure below. It helps explain why Yellowstone, despite its vast stores of heat and molten rock, remains so remarkably stable and doesn't erupt more frequently. The cap manages pressure, acting as a dynamic barrier that both contains and safely vents volcanic energy, allowing steam and gases to escape in a controlled way. Picture a giant, complex plumbing system beneath your feet. The main chamber is the furnace, generating immense heat, while the cap above acts as a pressure release valve, preventing dangerous buildups. This cap isn't a solid wall, but a spongy, ever-changing layer filled with molten rock, solid fragments, and supercritical fluids that move and shift over time. These fluids, especially the superheated water and gases, are crucial to the volcano's behavior, influencing everything from geyser eruptions to the release of heat. This discovery gives us a much clearer, more detailed picture of Yellowstone's inner workings, and helps explain why the region remains peaceful despite its fiery heart. The cap is a natural stabilizer, not a sign of imminent danger, but rather a testament to the volcano's long-term balance and resilience. With this new understanding, scientists can better monitor, predict, and assess Yellowstone's state of unrest, ensuring that we remain prepared for whatever the future may hold. To truly grasp the importance of the magma cap beneath Yellowstone, we first need to understand what it is made of and how it functions within the larger volcanic system. The magma cap is a slushy, superheated layer that sits about 2 miles below the surface. It's a fascinating mixture of molten silicate and porous rock, forming a kind of sponge that holds both heat and fluids. Within the tiny pores of this rock, you'll find supercritical water and gases, especially carbon dioxide, trapped under immense pressure. Supercritical water is a unique state, neither liquid nor gas, that can dissolve minerals and transport heat with remarkable efficiency, playing a crucial role in the underground chemistry. As magma rises toward the surface, gas bubbles begin to form, much like the fizz that escapes when you open a can of soda. This process is a key driver of volcanic activity. In many volcanoes, these bubbles can build up and drive explosive eruptions. But Yellowstone's magma cap behaves differently, acting as a kind of moderator. The cap is riddled with fractures and cracks, which connect it directly to Yellowstone's vast hydrothermal system of geysers, hot springs, and steam vents. This intricate network allows gases and fluids to escape gradually, acting as a natural safety valve that relieves pressure before it can become dangerous. Instead of pressure building up to catastrophic levels, it's vented in a controlled, steady way through the park's geothermal features. This is why Yellowstone, despite its reputation, isn't constantly on the verge of a massive eruption. The system is self-regulating. The balance between the magma cap and the hydrothermal system is delicate, but it's what keeps the pressure in check and prevents sudden, violent outbursts. Our scientific analysis shows that the amount of bubbles and melt in the cap is well below the threshold needed to trigger an eruption, providing reassurance for scientists and visitors alike. In essence, the magma cap acts as Yellowstone's buffer and regulator, absorbing changes and keeping the entire volcanic system stable over time. It's this remarkable natural structure that helps explain why the Yellowstone volcano remains calm and why its breathtaking landscape is safe to explore today. Discovering the magma cap required cutting-edge technology and teamwork. We used a massive vibrosis truck to send seismic waves deep underground. Over 600 seismometers captured the echoes, letting us map the subsurface in high detail. The breakthrough came with advanced 3D seismic imaging, using supercomputers to reconstruct the underground layers. The magma cap appeared as a strong, distinct reflector in the data, a clear, bright line. This clarity allowed us to identify and analyze the cap's properties for the first time. It's a leap forward in understanding how Yellowstone's volcanic system is regulated. Yellowstone's ground is always moving, rising and falling in a slow, rhythmic breathing. Uplift signals magma or fluid buildup. Subsidence means pressure is being released. We've tracked these changes for a century, now using GPS for millimeter accuracy. The most dramatic uplift was from 2004 to 2009, when the ground rose nearly 10 inches. Then, in 2010 it subsided, showing the system's dynamic cycle. This cycle reflects the constant push and pull of fluids and gases below. The magma cap gives new context. It likely flexes with pressure changes, causing surface uplift. As gases and fluids escape through the cap's fractures, the ground subsides. This model connects deep magmatic processes, the cap's behavior, and the ground movement we observe. It's the volcano's way of inhaling and exhaling, normal, not alarming. Understanding this helps us interpret Yellowstone's daily changes with greater confidence. Yellowstone is one of the most seismically active places in the U.S., with up to 3,000 earthquakes a year. Most are too small to feel, and are simply the volcano's normal heartbeat. Many quakes are caused by magma and fluids moving through underground cracks, creating swarms. At Yellowstone, these swarms usually signal fluid movement, not imminent eruption. By tracking these patterns, we gain insight into the volcano's inner workings. The constant tremors are a sign of a healthy, active system, not a cause for panic. When people think of volcanic eruptions in the United States, the dramatic 1980 blast of Mount St. Helens is often the first image that comes to mind. The eruption sent a massive plume of ash high into the sky, blanketing towns and changing the landscape in an instant. But Yellowstone and Mount St. Helens are fundamentally different in both their structure and the scale of their eruptions. While both are volcanoes, their behavior and potential impacts are worlds apart. Mount St. Helens is a classic stratovolcano, built up by layers of lava and ash. Yellowstone, on the other hand, is a supervolcano. Its caldera stretches for miles, dwarfing most other volcanoes on Earth. Yellowstone's last major eruption, which happened 640,000 years ago, was about 1,000 times more powerful than Mount St. Helens. It ejected enough material to blanket much of North America in ash, and left behind a vast caldera. However, despite its reputation, the most likely future activity at Yellowstone isn't a catastrophic super eruption. The park's landscape today is shaped by much smaller, ongoing geothermal processes. Instead, scientists expect slow-moving lava flows or small hydrothermal explosions to be far more probable. These events are much less destructive and tend to be localized within the park. The last lava flow in Yellowstone occurred about 70,000 years ago. It was thick, viscous, and didn't travel far, creating rugged fields that are still visible today. Hydrothermal explosions, driven by superheated steam, are the most immediate hazards in Yellowstone. These blasts can form craters and toss rocks, but they're small and highly localized compared to volcanic eruptions. While comparisons to Mount St. Helens help us frame the scale of volcanic hazards, Yellowstone's most likely future is much less dramatic and far more peaceful than many imagine. The real risks at Yellowstone are local, not continent-spanning. Most hazards are confined to small areas and are closely monitored by scientists and park rangers. Understanding these differences helps us focus on realistic hazards and appreciate the unique geology of each volcano. It also guides how we prepare and educate the public. Yellowstone's super eruption potential is extremely remote. It's the smaller, more frequent events that scientists watch for, ensuring visitors and nearby communities stay safe. The big question: is Yellowstone about to erupt? The answer is no. All current data show the system is stable and at normal background activity. The magma cap discovery actually reinforces this stability, showing the volcano can vent pressure safely. If pressure were to build rapidly, we'd see clear warning signs: intense earthquakes, rapid uplift, and major gas changes. None of these are happening. Yellowstone's main magma reservoir is mostly solid, with melt levels far below eruption thresholds. Super eruptions are rare and would be preceded by decades of dramatic warning signs. For now, Yellowstone is quiet, and there's no cause for alarm. Our confidence comes from relentless monitoring by the Yellowstone Volcano Observatory and partners. We use seismometers, GPS, and gas sensors to track the volcano's every move. New technologies, like advanced seismic imaging, help us map the subsurface in detail. We update the public regularly, using a clear alert system, currently at its lowest level. If unrest increases, we'll raise alerts and communicate clearly. Super eruptions are exceedingly unlikely in our lifetimes. The real work is understanding Yellowstone's complex system, piece by piece. By staying vigilant, we're prepared for the future, and can appreciate the wonder beneath our feet.